that's not true. Find the shortest distance from the point 1, 0, -2 to the plane x plus 2y plus z equals 4. Right now, GeoGebra can handle finding distances between objects in space. So you go into a problem, even something along these lines, knowing that there is an avenue that you can follow to find the correct answer without doing any of the work. Right? But that's not the point. You know, the idea is to be able to justify it using the multivariable calculus. Right? So what we want to do, again, distance, specifically the shortest distance, right? That's a measure of the distance formula. So the shortest distance, that's the optimization part of it. The distance part of it relies on what you know about distance in free space. And that is specifically that distance is equal to the square root of, you know, pick your favorite variation, the change in x squared plus the change in y squared plus the change in z squared. You could have x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Basically, it's the difference between corresponding components squared. It's just a matter of what form makes the most sense. All right. So since we're talking about the distance from a fixed point to really a variable point, if that makes any sense, a point that's in motion, the plane is a set of points that follow the relation of x plus 2y plus z equals whatever it was 4. What I could say is x minus x sub o squared plus y minus y sub o squared plus z minus z sub o squared. All right. So it goes back to how we defined in the equation of a line in free space, where we're looking for the difference between some variable point and some fixed point. Right. So the fixed point here would be 1, 0, -2. The x, y, z part of it would come from the equation itself. Now that's solely variable, but if you think about the equation of any kind of expression, it can be solved. The equation of an expression, geez, the equation involving multiple variables, you could always solve for one variable in terms of the others. Right. So looking at, and let me just highlight it in nice pinkish color. I could solve this for x. I could say x is equal to 4 minus 2y minus z. I could say y, I'd have to subtract and divide, but still doable. So 4 minus x minus z over 2. Or I could say z is equal to 4 minus x minus 2y. These are all possibilities in terms of solving. But you'll notice in each case, I have 2 free variables, right? In each case, there's 2 free variables, right? So what that's telling me is that no matter how I decide to work this out, I'm always going to be stuck with 2 variables, which makes sense because we've been working with 2 variables for a while now, right? You know, in college time for a while, like a couple of weeks. So what we can do is we can start saying, all right, well, which one do we like the best, I guess? Well, let's start plugging in some information here. Well, first, that worked out nicely. Do it that way. X minus 1 squared plus y minus 0 squared, so y squared, plus z minus -2, that's the same as saying, it's like the old Zima commercial. The same as saying z plus 2 squared. All right. So I have a distance model that I can call f of x comma y right now, as long as I get rid of the z. I could call it f of x comma z as long as I get rid of the y. I can call it f of y comma z as long as I get rid of the x. Right? I have all three of, or any of these three relations over here. I'll pick the color. Any of these three relations over here that can allow me to make that substitution. All right. So I just want to go with what I perceive to be the cleanest one. But it really doesn't matter which substitution I make, because it'll allow me to go from a function of 3 variables to a function of 2 variables, and that's never going to be a bad thing. If you can reduce the dimension of your multivariable function, that's always going to be considered a good thing. All right. So that's what we're going to do. It's just a matter of picking which one you like. All right. I like the idea of getting rid of z and replacing it with the xy equivalent. Right. You may disagree, and we're both right. I mean, I guess you might consider me to be more right because mine's the one that's ending up being documented here, but that's the only reason I'm more right. And also, I kind of like replacing the z because we're used to f of x comma y. So it lines up with our rules, you know, everything we've learned about first and second order partial, f sub x, f sub x, y, and all that. I don't have to rethink of it in terms of z, which isn't really that big of a deal, but for some people it is. All right, so I'm going to say d equals, and then we'll have the x minus 1 squared plus the y squared plus, instead of the z, you know, one thing I can tell you, I would never have swapped out the y, because y was already pretty simple, and I wouldn't want to make that more complicated. So that's the one thing I would have said. I would have said, I'm not doing this because this is already nice and simple. I don't want to make them more complicated. That's the only restriction that I would have had on this. Okay, but aside from that, you have carte blanche to be able to decide. So just making my substitution here. Like sometimes it recognizes the radical and sometimes it doesn't. All right. So now I have that expression on the right-hand side that's strictly in terms of x and y, which is good. If I wanted to torture myself, I suppose I could distribute out some of these binomials and clean it up. The best I'm thinking is, you know what, why not, while I'm here, combine the 4 with the 2. I mean, that's really all I got. All right. Now, we are going to want to make an adjustment to this before we start doing the calculus, just for convenience sake. And I'll show you what I mean by that in a second. Right? Because this would be something pretty nasty. If you had a chance, because, you know, like I'm well aware that my videos, when I post them during the day, they probably could be a little bit more timely, because, you know, I post them when I'm able to sit down and make the videos, because from year to year I kind of I get a little picky about how my videos are. Some of them are like, I kind of sound like an idiot in that one, let me redo it. And most of the time it's because the pages don't match up, and, you know, subtle things like that. But yeah, the videos today came up. I posted them around like 2 o'clock, 3 o'clock in the afternoon. So it's not unexpected if students didn't have a chance to take a look at them before class. But if you did, you noticed, whoa, crazy. Huh, pretty easy. Easy. Whoa. Extreme close up. Whoa. And then not too bad. But if you look at what we're differentiating here, not too bad. you look at what we're differentiating here, that's where the woe factor comes into play. All right. So what we want to do, based off of this that looks very woe right now, is come up with a way to make it not so woe. All right. So take it from whoa and make it more like whoa. You know, so if we could do that, then we're going to make our lives a lot more manageable. Yeah, coming in. Oh, okay. So we need a, I keep wanting to say vector value function. I mean, if we want to make this a vector value function, we could, but we don't want to. We want to make a multivariable function, but make something that's a little bit more user friendly. That radical is killing me. I don't want that radical. But what I can do is use my Pythagorean relationship and say, well, we know that d is equal to the square root of all this, but d squared is equal to all of that without the radical. Okay, and a natural thought would be like, you can do that? Yeah, you can square both sides. There's nothing wrong with that. It's just a question of whether it's going to get you in the right direction, get you pointed in the right direction, if you say. Right. And so what we're going to do here is define this as f of x comma y. All right. So this whole expression here is now what we're going to minimize. We're going to optimize this instead of the radical. All right. The rationale being, and like this is kind of this is my buzz phrase for describing this, but it's along the lines of, as the square goes, so does the number. But what I mean by that is, if we find the smallest squared value, then its square root value will also be the smallest, right? And since we're looking to minimize, we are looking for the smallest, right? So if in a number set, I'm looking for the relationship between two values, and out of those two values, which one is smaller, I could determine which of their squares are smaller. It doesn't seem to make sense in terms of like being overly helpful, but it'll get the job done. So let me just show you really quickly in a very simple, I keep wanting to say simplistic, but really simple sort of way. So let's say you have a set of numbers that we'll call n, and their corresponding powers of 2. So I'll put in some values, 0, 1, 2, blah, 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 blah. All right. And what I want to do is, out of this set of n values, determine which one is the smallest. All right. Well, let's say I didn't have access to those n values, and I could only look at the n squared values. So only looking at the n squared values, you would have to make a determination of which one corresponded with the smallest n. Out of 0 through 144, if I'm trying to figure out, without looking at the n column, which n squared column would correspond with the smallest n, you would probably say, well, I think the 0. And then I would say, why? I'd say, well, the square root of 144 is going to be bigger than the square root of 0. So I'm not really looking at what the square root of 144 is, just the fact that the square root of 144 is going to be bigger than the square root of 0. All right. So like 1 is less than 2 because 1 is less than 4, and 1 is the square of 1, and 4 is the square of 2. So those relationships, they're not, I was about to say proportional, but they're linked together. They're co-related or correlated. All right. So that's the idea here. You're allowed to do stuff like this, just like if it were the cube root or the 10th root. So like what I say, and it doesn't always land, which is why I go into this lengthy explanation, is as the square goes, so does the number. So as the root goes, so does the number. As the, like the cube goes, so does the number. Okay, so it's a really weird way of explaining it, but that's the best I got. What most people get from this is, all right, so you're telling me I can work with a simpler equation? Sign me up. We'll worry about y later. Right. So my new function f of x comma y is all this stuff. So if I want f of x comma, I already got f of x comma y. If I want f sub x, this is going to be a lot easier than if I had the radical there. Because if I had the radical, I'd have chain rule and chain rule inside a chain rule would have been something else, right? But here, yeah, there's chain rule, but it's not too bad, right? So what I'm going to do is I'm going to find some critical values, and if I need to, I'll use my second derivatives test. And need is dependent on a couple of things. Actual need, as in you have a bunch of critical values and you can't make heads or tails over which one is the one that you're looking for. And so you need some other resource. Or the other, it would be if you're specifically and explicitly asked to use the second derivative test. Right? So if I take the derivative with respect to x, it's 2 parentheses x minus 1. The y is irrelevant, plus 2 parentheses 6 minus x minus 2y to the first power times the derivative on the inside, which would just be a -1. All right. It's in our best interest here to clean it up, so I'm going to 2x minus 2. Now, this -1 can distribute along with this 2 to each term on the inside. All right, so rather than writing it as 2 separate steps, I'm going to do it simultaneously. All right, so -2 times 6 is going to be -12. -2 times -x is going to be +2x. -2 times -2y is going to be +4y. All right, a little housekeeping, I don't know. 4x plus 4y, like a -14. That's my f sub x. Now, we could set that equal to 0 and try to solve, but it's not going to get us anywhere just yet. We need our f sub y. Do that in blue on the side. All right, so the f sub y, the x minus 1 squared is irrelevant. 2y plus 2 times 6 minus x minus 2y to the first power times the derivative on the inside. 6 and -x are irrelevant, so we're just left with a -2. So same deal here. We can distribute a +2 and a -4 simultaneously. Oh, it's pretty terrible, but I'm going with it. Oh yeah, this is spiraling out of control. Oh, what a tangled web we weave. So 2y, so -4 times 6 is -24. -4 times -x is +4x. -4 times -2 is going to be +8y. All right. So barring any computational errors, which is always possible with this clown running the show, we're looking at 4x plus 10y minus 24. So f sub y would be 4x plus 10y minus 24. Right? And so we'd be setting each of those equal to 0 and solving. But the thing is, in and of themselves, no bueno. Right? We're looking at a function of 2 variables in both cases. all the other problems, I think, if I'm not mistaken, all the other problems had at least one of them where we could just solve for X in terms of a numerical value. It just worked out nice. This, or Y. This is not the case. I mean, we will still set them equal to 0. But we have to rely on the third part of the process for finding critical values, right? And that is, yeah, the first derivatives should be set equal to 0, but they should also be equal to each other, right? So this is the case where f sub x needs to be equal to f sub y, right? So we get from this a system of equations. Before I really dive into that, what I would want to do is get this in an appropriate standard form to make it easy on myself. So I'm going to add 14 to both sides here and make this 4x plus 4y equals 14. You can also divide everything by 2. That's fine also. I'm not going to, because we're going to use a matrix approach. Right? So this one would be 4x plus 10y equals 24. And I would say that we're using a matrix approach not because I want to. I'm sorry, not because I have to, but because I want to. Right? So I almost said that backwards. 4x plus 4y. Yeah, because it's easy enough to do this algebraically. It's just I want to refresh our memories on the bar-ref, reduced row echelon form technique, because it's going to become more and more prevalent as we go forward. In the first unit, it was kind of like, I don't want to say optional, but it was borderline optional. I thought it was still kind of useful, pretty useful, but it'll be more and more necessary as we go forward. Right? Never going to be a case where you have to do it by hand, but you will need to be able to use technology. Right? So we strip it down to its coefficients. So 4, 4, 14, 4, 10, 24. I cannot draw a straight line to save my life. One of these days I'll remember to favorite it. Maybe I'll just do that now. Desmos.com/matrix. Add to favorites. So I don't have to go looking for it every time. All right, so new matrix, 2 by 3, 4, 4, 14, 4, 10, 24. All right, then R ref on matrix A. Math frac, blast from the past, that's TI-84 speed, TI-83 speed even. Convert to fraction form. So 11/6 and 5/3 is what we're looking for, but we always put the row reduced form just as a way of putting appropriate work on the solution for a test, etc. All right, so I'll jot that down in a second. Let's see here. I'm at the part where I have to resize and respace and everything. Rethink my. You want to go home and rethink your life. I want to go home and rethink my life. Movie quote. Bonus points. Easter eggs, I call them Easter eggs. In videos, I sometimes drop little Easter eggs. Some people pick up on them, some people don't. But when I make a video, I'll make little movie references or little comments I call them Easter eggs. I certainly didn't make up that term, but and it has nothing to do with Easter. Well, I'm sure it originated in that, but yeah, anytime I drop an Easter egg in a video or a live lesson, it's worth a bonus point. So if I make a movie reference that you happen to know, or something that's easily looked up, all you have to do is, just like you would a typo, just state what the movie reference is or the TV reference, pop culture references, send it to me in the form of an email, and I will award you a bonus point. And then, the word of the day is coming, because I know I owe you, I believe I owe you 4 words of the day at least. So get ready for those. They're coming. So I haven't forgotten. I actually sent myself an email, a scheduled send email to come right before class started today to remind myself to do the word of the day. So that's coming also. And so just be on the lookout for those bonus opportunities. Right. So anyway, x is going to be equal to 11 over 6, and y is going to be equal to 5/3. These are our critical values. My equal sign is terrible, so I'm fixing that. Well, these are the components of our critical values. So our critical value specifically, if I can make a squiggly bracket, I'll check the chat in a sec. 11 over 6, comma 5/3. Now we just want to see, first off, since there's only the one critical value, this is dangerous territory, because this might be one of those trick questions where maybe there is no shortest value. Maybe this is leading to the longest value, which would be a disaster. But also, I do have to justify this. Close on that. So we're going to apply a second derivatives test to verify that this actually gives us a minimum distance. All right. So what I need is, well, second derivatives. So f sub x, f sub y, and f sub x, y. And then from there, we get the discriminant. Now, this is a good situation, because when you have a polynomial-based function, whether it's the world's most hideous one or, less so, it's going to be easy to find second derivatives. The first derivative, we had to do a little bit of work, and the second derivative is not going to be challenging at all. All right. So f sub x is really just going to be a 4. F sub y is just going to be a 10. Right, because we're only just taking the derivative for the f sub x, the first function with respect to x. Respect being the first word of the day. Respect. Right. So the second function, the f sub y, is only related to the 10. Get my little mouse out. So that part's easy enough. Now the f sub xy, that's the first order partial with respect to x, now differentiated with respect to y. So we're going to get a 4 there as a result. All right. Now it just begs the question, is that an appropriate answer for the mixed second order partial? I recommend you have a quick look at f sub yx and make sure it gives you the same thing, because if you're dealing with a continuous differentiable function, then you should be looking at an f sub xy and f sub yx being the same thing, right? And it turns out that they are. So my discriminant is going to be the product of the first two, so 4 times 10 minus, can't get a minus sign in here with my mustache, minus 4 squared, if I could ever get this to work right. Minus 4 squared. Right. So the first two multiplied minus the last one squared. But really, we talked about this last time. It's actually the first two second order partials multiplied minus the last two second order partials multiplied. So the homogeneous second order partials, f sub xx, f sub yy multiplied, and then the mixed f sub xy, f sub yx multiplied. It's just because f sub xy and f sub yx are the same thing. We just take one and square it. So we're looking at 40 minus 16, or quality 6, result 24. And so now based off of this, I can make a determination of really what's going on with that critical value. Right now, it turns out, and it's kind of this is the best possible scenario when it comes to the second derivatives test. If you have a single critical value, right, just one critical value, and usually when that happens, it corresponds with instances in which the second order partials are constant, then whatever conclusion you draw is specifically related to that critical value, right? So that then there would be no confusion, right? So the first thing we note here is that the discriminant is positive, right? If the discriminant were negative, it would be a saddle point. If the discriminant was equal to 0, the second derivative test would have let you down. It would have failed you. It would be inconclusive, which is the worst possible outcome. Okay, because that means that maybe there's an answer that you can get. We just don't know it. Okay, so here we know we're going to get an answer. Now we go to the next level and say, okay, well, what is the sign of my second order partial with respect to x? Right, so f sub xx is positive. And when f sub xx, so when your discriminant is positive and your f sub xx is positive, then we're looking at a local minimum. All right, there's that reverse relationship between the second order partial sign and whether it's a max or min. So, you know, that part is, it's always throwing people for a loop, but it's very consistent with the second derivative test in Calc 1. You know, like the sign of your actually, yeah, no, it is a second derivative test. It's the when you take the second derivative and you plug your critical value in, if it ended up giving you a positive sign, it was a local min, negative sign is a local max. That actually has its origin story, if you will, in this second derivatives test. And I did promise, I think last class, maybe 2 classes ago, that I'd give you the origin story behind that. It's coming. It's just it's one of those things that I'm going to continue to tease until we actually get there. So we're not there yet, right? But we do know that we're on the right path to finding a solution. We know that this critical value will give us a local minimum, which is great, right? So now we go back the rest of the way and say, okay, so now I know x and y, right? So we have a local min at (11/6, 5/3). So what I would then do is evaluate my function f of xy. Instead of f of xy, I would say f of 11/6, comma 5/3. All right. So what I do is I take my f of x model, which is way back over here, and replace each x with an 11/6 and each y with a 5/3, which is terrible. And it's not that bad. But if I had no expectation that anybody would have time to watch my videos from today. But if you did watch them, what I'm about to say is going to sound very familiar. If not, then there you go. You'll have picked up something even without having watched the videos. So instead of writing it in as x minus 1 squared, and we've done this before as a class, so it shouldn't be completely boring. But x minus 1 squared plus y squared plus blah, blah, blah. I'm going to use a's and b's instead of x's and y's, right? The reason why I'm going to do that is because for substitution purposes, if I needed to pop in more than one value for a and b, then this is going to be the avenue to help me accomplish that goal, right? So there's the element where it's there for substitution purposes, like it'll help me get the answer, right? So that part is useful, but also I want to have the ability to verify that it is in fact going to give me the smallest distance, right? So first off, I'm going to get the number. So we'll start off with that. 11/6, 5/3. Right? You can put it in fraction form, decimal form, doesn't matter. Right? So anyway, I get 25/6 here as a result. That result is d squared. Now they were asking, find the shortest distance. All right, so I need d. So square root, I'm only going to care about the principal square root, so the positive square root, so 5/rad 6. All right, so that would be my shortest distance. All good. But the big question that I would have as a student was like, all right, I mean, I could have substituted that in a scientific calculator. Why the hell do I have to do the A and B stuff? Right. So let me go back here for a sec and default it again to like 0. Just so I have my sliders. All right. Now 5/rad 6 is about 2.04 roughly. So what I want to do here is first make this into a radical. So I'm going to slap a power of 1/2 around the whole shibbity bangity boomity boom. If it lets me. And I'm only going to do a power of 1/2 because it's not easily going to let me do a radical over the whole thing, right? So that is what my distance formula would be with any constant value substituted in. So what I would do is use my slider and just slide around. Slide my B value around, slide my A value around, slide them both simultaneously, and just do a quick visual. And really, you don't even need the negatives. Well, I guess you could use the negatives, but I'm just looking at the, at least for the A value, maybe not, and even the B value, because it looks like that plane is living kind of above the XY plane. So I'm expecting positive numbers, but just to play it safe, maybe leave the negatives in. But if you can restrict your domain, it might be for the best. But what I'm going to do is I'm going to animate this. That sounds too fancy. I'm just going to hit play so that it moves. And I'm just going to look at those numbers as they're changing and see if there's ever a moment in time where it gets to around 2, in the neighborhood of 2. And so it looked like right in this neighborhood here. So living over here somewhere, it gets around 2. But I don't see any evidence to indicate that it'll ever get below 2.04. All right. So what this is for me, it's not anything empirical. It's more like just a quick visual of, does my answer make sense? That's really all I'm looking for. Because if you're looking for a line segment connecting a point in a plane, you could have a lot of different possibilities. You could have this one. You could have this one, or kind of. you could have something like this one. But what we want is the shortest, so we're probably looking for something like this one. All right. What this model does is it gives us the distance from that point to any point along the plane. But by using the multivariable calculus, we're able to minimize that distance, all right, and come up with that shortest distance, which is about 2.04. All right, so it's pretty cool, but also obviously intricate, right? So what I wanted to do is steal this example and just kind of go back in time for a few minutes and just show you the vector approach for this, like I said I would do weeks ago, and I'm finally paying that off, right? So, and I'm about to give you another typo opportunity here. So let me do that. So I just want to do this real quick. All right, so on page 26 of the Unit 1 packet, we would actually replace the problem that's there with this problem. Right, so that would be the typo for somebody. Typo opportunity. And again, hey, we've already talked about how this page wouldn't even be in Unit 1 anymore. It'd be in Unit 2, but I actually still want to change the problem itself. Okay, so this is a blast from the past, but the idea here is for us to have a much shorter way of doing it, but also not for the purpose of replacing what we just learned, more so as a supplement, a checking mechanism, and also, you know, for lack of a better term, a way of appreciating both methods. You know, this brings something to the party that the other method doesn't, and the other method brings something that this does. You know, so if you look at, and we'll just focus on the formula for now. It's the dot product of QP and N divided by the magnitude of N. Oh, sorry, let me just pause for 1 second. Yeah, sorry, I'm trying to impress upon my son the need to study vocabulary words before his mother gets home and destroys him. So, you know, he doesn't quite get it. He'll see soon enough. But yeah, it's the thing. Like, I very rarely, I don't do the parent soapbox thing, because I definitely don't have all the answers. But one thing I do have the ability to do is see into the future and know when somebody is destined to be like utterly annihilated. And honestly, not having your homework done by the time mommy gets home is the quickest way to end your evening unpleasantly. Studying is part of that. Come on, move it. Anyway, so we have this whole component QP in the direction of N. And so, or at least that part of it, that changes into this formula of D equals QP dotted with N over the magnitude of N. And so it's like, well, first off, how do we get from one to the other? And the other is, right, now that we have that, what do we do with it? And how's that going to get us our answer? Right. So we have this diagram here. And this diagram is trying to give us the distance from a point in space to a plane. All right. So the thing is, we have no idea what point on that plane would correspond to the shortest distance or the shortest line segment connecting the plane and the point in space. All right. So this is really what we want. And this one over here is this is the ideal vector. We want this. All right. But what we might end up having is this. All right. So we might be stuck with this. Which means, and you know, like you look at it and say, well, what's the difference between one line segment and the other? Well, they'll both connect the plane and the point in space, but one of them will do it in the shortest possible way, and the other is not that. All right. So, but what we can do is we could actually use that information to get us where we need to go. All right. So we can get a displacement vector between Q and P. If we have the plane, we already have the equation of a plane, we already have its normal vector. All right. So what we can actually do is find the dot product between the QP, that point, arbitrary point on the plane, and the point in space, that vector, and the normal vector. All right. By dividing that by the magnitude of n, what we're doing is we're finding essentially the component of QP that's acting in the direction of n. Right. And so by using that idea, we're actually, and since all of these vectors would be parallel to one another and also have the same length, we would necessarily be finding the thing that we're looking for. Right, which is the length. Once we find its magnitude, the length of RP. Right, so it's kind of weird in that regard. RP, that R is designated as just some random point, not R for random, but I'm just calling it that. Some random point on the plane that's associated with the fixed point out in space. Okay. All right. So what we can do here, and we can work in general terms, but I think the idea here is to come up with a method that's going to allow us to not have to work in general terms. All right. So we can look at the plane. The plane has a normal vector of 1, 2, 1. All right. So remember, it's AX plus BY plus CZ is equal to some constant value D for constant. All right. So we have our normal vector. That part will never be the problem. If you got to find the shortest distance between a point and the plane, and you're not given the plane, then there's nothing to solve. Then on top of that, like if you were given the plane, then you're automatically really given the normal vector because you just need the coefficients of X, Y. So that part works itself out. Right. Now QP, well, we have the point, this point out in space, which we call P. Q is just some point that we know is on the plane. All right. So it could be any point. All right. So Q is a point on the plane. All right. So Q would be in the form of X, Y, and Z. Right. If we wanted it in general terms, that's actually what it would be. Right. So that's how we're going to work with it initially. But then we'll actually make it numerical, specifically numerical, and then go from there. Right. So we have that information. We also need the magnitude of n, which is 1 squared plus 2 squared plus another 1 squared under the radical. Under the radical, crying out loud. All right, so 4, 5, 6, rad 6. All right, so that's a wonderful development, because if you remember, our answer previously had a radical 6 in it, so at least we know we're gonna get part of it. right? So we would want to dot Q, P, and N, right? So QP is vector QP. So the displacement vector would be x minus 1, comma, y minus 0, comma, z minus -2. Starting to look a little familiar, I think, hopefully. Right. So we're taking that and dividing it by the square root of 6. Right. Now, and then finding its magnitude. All right. So this is an absolute value symbol. And honestly, I know that you can go back and forth when you use magnitude, the notation for magnitude as a double bracket or a single bracket. I honestly, if I'm being completely, so to overuse the word honest in this case, you know what? Second word of the day, honest. I have no idea why I opted to go with a single bracket. All right, this should be a double bracket. It's correct either way, but I think it's honestly confusing. All right. So we're finding the dot product of QP and N. All right, so let's dot QP and N. I'm using some color coding here. Bear with me for a sec. So we're looking at x minus 1 plus 2y plus z plus 2 all over radical 6. Right? And so now we have a model that allows us to determine, and we'll get to the magnitude part in a couple of minutes, but we have a model that allows us to determine the distance from the point to the plane depending on the value of x. So, or I'm sorry, x, y, z, whatever your point Q is. And so now what we need to do is decide on a point that's in the plane. Right. And the good news is it doesn't matter, right? Because regardless of what you choose, QP will naturally be either stretched or shrunk in order to accommodate its distance from the point in space. And what'll happen is proportionally, its component in the direction of the normal vector n will change accordingly, right? So if I pick something that's really, really far away versus something that's really, really close, the component in the direction of n related to QP will naturally be adjusted to account for that, all right? So what I just need to do is choose a value that follows this model of x minus 1, y, z plus 2. All right. So it's like, well, easier said than done. Well, if I do that, going back to the original plane equation, if I'm just looking for a point that falls on the plane, I can really decide on anything I want for x and y. So why not just choose the easiest possible value or values? Right. So for example, I'm going to let x and y equal 0. Because I could let it be anything. The plane is infinite. It's just now it's going to restrict what z can be based off of that information, right? So if I know, oh, I gotta turn this off. Let me do that. All right, so let's say I let it be x equals y equals 0 in this original plane, which was modeled as x plus 2y plus z equals 4. So 0 plus 2 times 0 plus z equals 4, which would make z equal 4. Right? So we know that there's a point 0, 0, 4 is on the plane. Any ordered triple that satisfies this equation is on the plane. Right? So I could have let x and y be 1 and -1, pi, e, whatever. That would change the value of z, but as long as whatever you come up with for z satisfies, along with your choices for x and y, satisfies the relation, then you have a point on the plane. Right? So that works out beautifully. And so now all I would need to do is substitute these corresponding x, y, and z values in. Right? So using my highlighter again. I'd be looking at 0 minus 1 plus 2 times 0 plus 4 plus 2. So then we get 5 over radical 6. And I was actually worried that this would happen. Yeah. Oh, which way am I? Oh, wrong notes. Be right back. Yeah, I am a schlemiel. You know what? I got to go full blown schmuck on this one. There was I now remember why I had absolute value brackets here. I can't get out of my own way sometimes. I don't know. The reason why there were absolute value brackets is because there are absolute values, not magnitude. Dingus. Yeah, that's my bad, folks. I misremembered the formula, and in the moment of truth, I thought I caught my own typo, and in the end, I created a new typo. I created the very thing I wanted to destroy. Another movie reference. Actually, that one's from about 4 different movies, so a lot of different things, a lot of different possibilities there. So apologies for that one. I have nobody to blame but myself. Yeah. Sometimes the only thing you can do is just say, I done effed it up. But in the end, it is what it is. So 11 would be out. We wouldn't be really concerned with that one. Because it doesn't, I mean, it's a good problem, don't get me wrong, but it doesn't really fit in with the flow of this lesson, which already has kind of lost its flow. But this piece, this actually ties in. You see, after we did the previous example, this ties in a little bit better with what we're talking about, right? With the multivariable stuff. Right? It's a nice little connection piece. And what I am going to talk to you about, I'm trying to think when. I don't think it's next class. I got to look at my calendar. It's either the class after that, or it's right in the beginning of Unit 3, is how this connects to the multivariable stuff. Right? So there is that connection piece that actually shows us how we get from here to the solution to that multivariable function that we just worked on. So it's kind of cool in that regard, or at least hopefully you'll agree that. All right, so that's that. Now